Welcome to the channel. The problem is given on the operational amplifier. The gain of the circuit is given minus 1 upon omega RC. We have to find out the modification in the circuit. To introduce a DC feedback is to add a resistor. I am drawing the same circuit here. This is resistance, operational amplifier, inverting, non-inverting terminal, feedback capacitor. This is output voltage. Input is applied at inverting terminal of the operational amplifier. This is resistance. This is capacity. The voltage here V minus. Non-inverting terminal is connected to ground, and this is V plus. So first point, as per the virtual ground concept, V minus is equal to V plus, and as we know that the non-inverting terminal of the operational amplifier is connected to ground, which means 0 volt. The second thing, we have to apply the KCL at this node. I assume this is IR current, and this is IC current. So IR is the incoming current to the node V minus, and IC is outgoing current from the V minus. So IR is equal to IC. Incoming current is equal to outgoing current. I explained the KCL and KVL, also the capacitor working in previous videos, and providing the link in the description box. Now let's start. V in minus V minus by R, that is nothing but IR, and current flowing through the capacitor is nothing but C, differentiation of V minus minus V out by dt. So after solving, what we are getting, V out is equal to minus 1 by RC integration of V in into dt. So this type of circuit is nothing but the integrator, and this is ideal integrator. The gain is provided, which is equal to minus 1 upon omega RC. From the equation we know that the gain is minus 1 upon RC, but this gain is frequency dependent. That's why gain is equal to minus 1 upon omega RC. We have to consider the high frequency and low frequency. What happens at high frequencies? If the frequency is high, the reactance of capacitance depends on the frequency, and that is 2 pi fc. So this reactance is equal to 1 upon 2 pi fc. So if high frequency, which means that you can imagine ideal one like infinity, 1 by infinity will be 0, this will be short circuit, which means that if there is high frequency, capacitor will be short circuited. But what happens at low frequency? If it is low frequency, the frequency is low, ideal say 0, 1 by 0 means infinity, capacitor is open circuited, and if the capacitor is open, the op-amp goes into the saturation state since the open loop configuration of the op-amp, and this is unstable behavior. And to avoid this, what we have to do, we need to take one resistor in parallel to the capacitor. Say this is feedback resistor. So the various options are provided. Out of that, fourth one is right. We have to add a resistor parallel to C. What happens at low frequencies? If frequency is low, the capacitor is open circuited, and what gain we are getting at low frequency, that is nothing but minus RF upon R. The input is at inverting terminal, so negative. The feedback resistance and the input resistance, capacitor is open circuited at low frequencies. So this operational amplifier at low frequency simply like a amplifier, inverting amplifier, getting the stable behavior of the operational amplifier. We are getting more stability than the ideal integrator in the practical integrator if you are connecting resistor in parallel with capacitor. So this is the solution. We can again calculate the gain. We can calculate the gain by taking resistor in parallel with C in the feedback, IR, which is equal to the summation of I RF plus IC, and what gain we are getting in this case, minus RF upon R in bracket into 1 plus J omega RFC. After solving, this equation I is equal to IRF plus IC, what we are getting, gain is equal to minus RF upon R 1 upon 1 plus omega RC, which means that at low frequency, when this capacitor is open circuited, the RF comes into the picture, and this amplifier simply acts like an inverting amplifier with the gain minus RF upon R1, getting more stable behavior in the practical integrator. The solution to this problem is option 4, take a resistor parallel to C. Thank you.